The following program is brought to you by Caltech.
Yes, I hope it will answer some of the questions I've heard lately from Kim and from others. I'm David Mimoun, so I'm at ISAE, University of Toulouse. So I'm not a seismologist, but I've been lately, well, since 10, 15 years, very much interested in seismological instrumentation. And I would like also here to acknowledge the contribution of Philippe Lognonnet and Raphaël Garcia, who have been providing, let's say, most of the second part of this presentation. So after a brief introduction on planetary seismology and to recall some seismology basics, because we've got fellow distinguished seismologists here, but not all the people here are seismologists. Basically, the presentation will be split in two parts. One which will be more dedicated to the classical seismology for Venus, which is how do we need to deploy a seismometer and what are the constraints to deploy a seismometer on the surface of Venus. And the second part of the talk will be more dedicated to less classical ways of doing seismology with infrasound measurements or even remote sensing seismologies. That's the way I put it. During these two parts, I will try to talk about first the underlying assumptions that we've got, and then a little bit about the theoretical background, especially for the second part, for you to understand where we come from and where we go, and eventually all the constraints, because I'm also much interested in making an actual payload. So what are the system constraints that derive from this type of measurement or this type? I think it's also interesting when you keep in mind that you want eventually to fly this kind of mission. So my first slide is a kind of related to my interest in this planetary seismology. There are many reasons why we want to do seismology, but one of the most interesting point of view, I think, from this perspective is when you go back to the Apollo heritage and the deployment of the 3 seismometer network on the Moon. Most of what we know from the story of the Moon Earth system and the initial conditions and the actual consensus that we have about that comes from seismology. The first instrument deployed by the astronauts on the Moon was a seismometer, and together with the study of the rocks on the surface, the constraint that the seismology has put on the internal structure of the Moon actually gave us the general idea or the actual consensus that the Moon comes from an impact. So that's seismology and planetary seismology provides very strong constraints on the story of planetary bodies and telluric planets. That's a point I want to make. And we expect to have the same kind of thing for Venus, and I hope we will be able to fly within a foreseeable future seismology experiment of Venus for the same kind of reason. Because as you know, in the 2000, there has been new developments about the first ages of the solar system with the so-called Grand Axe scenario, the NIST models, saying basically that all the outer planets have been moving back next to the Sun up to 1.5 astronomical units, and therefore limiting the growth of Mars. And when they came back, eventually they all disturbed the cometary swarm, which were rich in ice, and eventually enriched the internal planets, Earth and Venus, in water. So we expect also to, with this, if we know the internal structure of Venus, we will be able to provide some additional constraint to this story. And Dave was saying about connecting the dots. So all about this story is about connecting the dots of this grand history of the solar system. So that's why I'm very interested in that, and that's one particular point I wanted to make. So planetary seismology, for me, is also tells the story of the solar system. So from a seismometer deployment point of view, where are we today? So on Earth, fortunately, you see here the dots that I found on Earth. We've got more than 20,000 stations. I don't know if it's completely accurate. Probably people will be able to discuss that number, but we've got thousands of stations enabling us to have more than a structure. We go into tomography, and so now there is a very good knowledge of the interior of the Earth, and we go into 3D modeling and stuff like that. From the Moon perspective, you've seen in my previous slides, we have been fortunate to have the seismometer network operating in the 70s, so the 3 seismometer. Unfortunately, not on the far side of the Moon, so there are also studies that want to put a seismometer on the far side of the Moon to put additional constraints. But we've got also some insights about that. For Mars, after the trials on the Viking lander, you know probably, and Bruce is here, we are working very hard to have our first real seismological station on Mars, a very broadband seismometer, and Philippe is the PI also of the seismometer. We're working very hard to get the very first station operational on Mars with all the companion sensors that are required to get, all the constraints that are needed to do good seismology on Mars with a barometer, with a magnetometer, temperature sensors, and so on. So this is where we are. So on Earth, on the Moon, on Mars. And what about Venus? So it took more than 20 years since the latest try on Mars to get a seismometer. On Venus, there is nothing, and this is obviously something, well, last piece of the puzzle, as we have said before. So the first idea to do seismology on Venus is to use a classical seismology. So after Shira, I've put this slide together in order to explain what will be the constraints eventually on a seismology payload. So seismology basically use the transmission of wave through various materials to derive the structure of the medium seen along the path. So when you've got an event of planetary magnitude, either a quake or a meteoritic impact, this generates seismic waves, which are waves in a continuous medium, and this takes some time to travel through all these materials. You see here a picture of, for instance, of a planet, and this takes some time, and at the interface between the various medium, you've got things that happen, transmission, reflection, so that eventually the signal that you get in a single point on the planet is a composite of all the waves coming up here. And you see, and we record the ground motion at an arbitrary point on the planet with a seismometer, and this eventually gets the seismogram. This is a time-varying function of the acceleration of the ground. So basically, classical seismology needs to be on the surface and record the ground motion with something which is the seismometer. So therefore, what is a seismometer? So a seismometer, for people not familiar with this kind of instrument, is just a very, very long period, very sensitive accelerometer, which measures the ground motions. And it's most of the time based on analog principle. That's not a very digital or stuff like this. This is most of the time analog electronics. And this is not a cool payload. I mean, there is no 3D images, no laser shooting on Mars, nothing like that. So that maybe explains the time that we had taken to fly one on Mars. But there is something which the seismometer enables measurements that are not feasible by other planetary payloads. If you take ER imagers, spectrometers, they give you information on the first microns of the surface. when you measure the neutrons, you get a few centimeters up to 1 meter. With GPR, ground penetrating radars, you can go to, depending on the properties of the surface, you can go to several kilometers, but you stay very much superficial. So you've got the boundary conditions of your planet. You've got, when you, with a seismometer, as the wave travel through the planet, you've got a sounding down to the planet core. And this is why it's so important to do that. And in order, during a long time, and this was done with the Apollo station, we thought that we need at least 3 or 4 stations to get these measurements done. So that led eventually to big missions, big flagship missions with a lot of landers, net landers with four landers or other missions. This was done typically with a classical ray inversion where we were measuring the arrivals of the various rays through the planet at the various positions, and in a way similar to the GPS. Therefore, we will be able to get the internal structure. Now, and this is the best example is the InSight mission. Now we are able to do seismology with one station and get very much the same information with little a priori information with with surface wave study with typically two kinds of measurements, the study of the surface waves and the various arrivals of the surface waves, and the normal mode inversion with an a priori model and with a big event. But basically we are able to do what required 3 or 4 stations on the surface of the planet with only one, and that's a big improvement with respect to that. And the observable that you derive from that measurement is the seismic velocity as a function of the depth of the planet, and in the lab you can derive all the properties of the material that you get from that seismic velocities. So that's basically where we are. And if we go to Venus, we will probably not be forced to, for instance, on the ground, to go with several stations or network of stations, but using an InSight-like one station measurement that could be good enough to get the job done. What is really important also when we start to think about a seismic experiment on the planet, and Dave went through that, another version of that figure, is about the assumption on seismicity. Because as the seismometer is basically an accelerometer, so you've got eventually a signal over noise ratio that you have to consider, and you have to measure the signal which is the ground motion against the noise of the environment. And in order to do that, you need to first the more sensitive you are, possibly, then the more quakes you will derive, and the more observable you will feed into your model. So the more sensitive the seismometer is, the more quakes it detects. And so you are trying, so that's the reason why you are trying to get most sensitive seismometer, but you have also to take into account the environment that will prevent you to record what you want to record, because you need a certain number of events, of quakes, in order to inverse your model. The issue with Venus is that, Philippe, in the 3 trees for seismology has put numbers. I've found one number in a Stofan proposal. So this is very complicated. But basically, I think that a reasonable assumption, this is Mars seismicity, this is the Earth seismicity, is that probably we can assume some kind of seismicity between Earth and Mars. That's the reasonable, but this will be discussed later. But this is very important because this will size the whole system, actually. The other thing that is important is the fact that the occurrence of quake is a probabilistic process. You cannot predict quakes, but you've got a rate of quake that arrive at a certain period, at a certain frequency, and eventually there is a dependence between the time you wait on the planet and the number of quakes you detect. And the more sensitive your seismometer is, the less time you need to measure the number of quakes that you need to inverse your model. And so that's not very good for us on Venus, because you can work on the noise on the noise floor of your instrument, but eventually you need a certain time to get the number of quakes you need to inverse the models. So that's the reason of the long-lived stuff. And the point is that even if you do a very good seismometer, you will be also eventually limited by the environment, which is something we studied into details for InSight. The environment plays a big role also in this threshold value. You cannot go below a certain value because this is the noise of your environment. The good news is that if you can wait longer, even if your instrument is bad or if your assumptions about the noise of your environment is bad, if you wait longer, if you're able to wait longer, then you can recover. We are not falling off the cliff. We're not, it's not just like you're not taking the good picture if you're disappointed. You just have to wait longer, which is eventually an issue on Venus. So how does it derive on the Venus long-lived lander? So we have been doing this exercise on InSight, and this is a preliminary thing that for you to understand what kind of constraints play into role when you look at the signal over noise ratio that plays into this noise performance. Basically on Venus, what we will have to take into account the instrument self-noise itself from the sensor head. We have seen pictures of seismometer deployed, so it will have a noise, intrinsic noise floor. But you have to take into account all other noise, such as the sensitivity to the environment. If you're sensitive to local magnetic field, to temperature fluctuation, stuff like that. You have to take into account the noise, the EMC noise coming from the various parts of your system, especially in the lander noise. If it happens, if we want to put a Peltier cooler on the lander, that's okay. But if we have an ASRG which oscillates at 1 Hertz, this is not good. And eventually, we have also to take into account more general effects coming from the environment, general environment of the planet. For instance, we cannot exclude the fact that there are major pressure waves coming and going precisely in the frequency band of your interest that might hide some seismic signal. So typically a pressure effect which ripples into pressure, into tilt on the seismometer and prevents us to see what we want to see. So there are a lot of effects that may play into the game when it comes to the instrumentation. How not to forget stuff? We've been developing a sort of approach on InSight that might be applicable to Venus. Basically, we are just looking at all the possible environment constraints, all the subsystems of the instrument, and we check in each at each intersection if there is a potential noise. This is a far more systematic approach than others, and that help us to build confidence in a model that we might not have forgotten something that prevents us to get the job done. So we probably, during the workshop, use that kind of map to help us to derive the various contributors to the noise system of the seismometer. So, all in all, for what are the technological challenge for a Venus, seismometer which stays on the ground? So there are two challenges. First, to reach the sensitivity and the bandwidth that is required to measure seismic waves, and then to reach the required duration for the measurement. And that is as much as important as the first one, because if you've got a seismometer which is very sensitive, which lasts 2 hours, that will not make the job. So these are the two conditions required to get a seismology experiment on Venus. So mechanical design can be very simple and robust. We know that, you know, basically it's a mechanical pendulum is very good, so that can work. Electronics, as we discussed, is a more difficult issue, even if that's probably not the most difficult issue, because we're talking about very robust analog feedbacks and stuff like that. If we want to go to a very broadband with a geophone, we even probably don't need feedback. So that's not something that sounds not feasible, even with the constraints we just allowed. So we can make preliminary guess, very wild guess actually, on the kind of sensitivity we have to reach when compared to Earth or to Mars. And let's recall that we can still have a trade about between a broadband VBB, a broadband seismometer, or a geophone that might do the job to some extent. To reach the required duration for the measurement that eventually derives from the number of quakes that I mentioned earlier, basically this is more complicated because you have to provide power, data processing, communication for, let's say, something between 6 months and 1 year. We're not talking about days, we're talking about weeks, months, and we need months to get to the requirements, to get to the investigation. There are also some possibilities. We can think also of more complicated ways of doing seismology, such as putting, you know, 2 stations and studying the green functions between 2 stations. I think that Walter Kiefer was interested in that approach that may require that may not provide overall constraints on the planet, but that may help, and that would require maybe only geophones or less sensitive seismometer. So that's also a possibility. All in all, what we can say is that sustaining a Venus probe and the seismometer about 1 year at 500 degrees and 90 atmosphere is a significant challenge from that perspective, even, you know, with the background that we have from inside and from other planetary missions. So what can we do? And part of the answer comes from Philippe teams. The story that I told you earlier is probably not complete. So you recognize the start of my previous slide with the travel of the seismic waves along the media, but the journey is not at its end on the ground, because actually there is a coupling between the seismic wave on the ground at certain frequency and the atmosphere. So the travel of the seismic wave for some frequency is not finished yet, and therefore goes on up to the ionosphere, and we will explain why later. So if we are able to get measurements of these waves either somewhere in the atmosphere or higher in the ionosphere of the planets, we can also do somehow seismology. And this is the reason, this would be an alternate way of doing seismology. So what is it about? Long period waves coupled with the atmospheric gravito-acoustic, that we can say acoustic waves, propagating upward in the atmosphere. So that there are a lot of papers from Philippe's team and others talking about that. And thanks to actually the thing to understand is that even if you've got a very small motion of the ground of, let's say, millimeter range for seismic pulse or for surface wave, Rayleigh waves, on the conservation of energy along a ray makes and coupled to the decrease of the density of the atmosphere, the very sharp decrease of the density of the atmosphere, makes that the motion of the atmosphere has to increase a lot along the ray. So basically, if we've got a very small motion of along at the interface of the surface and the atmosphere, and you've got a very small motion, this gets amplified by factors, very huge factors, when you go up in the atmosphere. And you can eventually detect it through ripples. If you are able to measure it in the atmosphere, that's good. And the first detection have been made through the impacts it has on the ionosphere, because this is the neutral atmosphere motion, but the neutral atmosphere moves also all the species that are not more neutral in the ionosphere, and also disturbs the chemical equilibriums. So you've got a cascade of events that happens in the ionosphere that can be detected. And with a proper filtering, of course, there are a lot of perturbations around that. But a proper filtering, knowing what are the frequencies we're looking at, this can be detected. I will not go very well into the theoretical background. So the theory of acoustic gravity waves come back in the 60s. And there have been a lot of work by Lognone, Artru, et al. In the last decade. But basically, the thing to recall is that if you consider the eigenmode of the planets, you see just like a bell, the planet rings after a big seismic event. So these modes can, over a certain frequency, can couple with the modes of the atmosphere. And so Philippe made the coupling between these modes, these eigenmodes of the planets, which rings, with the modes of the atmosphere, and over a certain frequency, these modes propagate up in the atmosphere, and we are therefore able to detect it. That's the theoretical background of all this stuff. We can discuss that, but you can refer to the paper if you want some more details. So what does it mean for us? It means for us that we can first put a seismometer on the ground, very first way of doing seismology. But if we're able to get the sensitivity required, and we can also try to get the signal when it goes through the atmosphere, better as following Jeff's request, over the top of the clouds, in order to avoid difficult situation for the technology. So if we can put a barometer over the clouds, or some kind of barometer over the clouds, we can detect it, or even from orbit, if we are able to detect the perturbations in the atmosphere with the required sensitivity, and if we are able to filter them in the bandwidth of interest in order to reject all the perturbations that might arise, that might be the job. So what is the situation of Venus? On Venus, so the proof of concept has been done on Earth, as we will see later, but on Venus, for the propagation of these seismic waves is indeed a competition between two effects. First, there is an attenuation due to the atmosphere itself, to the carbon dioxide atmosphere. So when you've got a waves due to viscosity, molecular relaxation, and some other physical processes, you've got a dissipation of this wave. But on the other hand, as I said, there is an amplification. Due to the sharp decrease in the density. So on Venus, we've got a competition between these two effects: attenuation of the wave that goes up, and amplification along the ray, due to the decrease in density. And we are most fortunate, because if on Mars the attenuation is very strong, on Venus the attenuation is not so well. Is more important than on Earth, but to some extent it allows the propagation of waves to a certain frequency precisely in the range of interest in the middle atmosphere. So, and this work was done by Raphael here. So this is the acoustic wave amplification as a function of altitude on Venus. So you see here that if we go to 60 or 100 kilometers, we still get sensitive amplification of the seismic wave, and we might be able to get an interesting signal in this range of altitude. If we get higher, the filtering goes up, but there are other ways to get the signal. Another thing we have to consider also when we have talked about the surface wave that goes along the planet and that eventually moves locally. The ground shakes the ground. The classical ray seismology is not completely dead also, because as you see, the P wave at the interface may transmit, so you've got a transmission at the interface, and also the shear waves, the secondary waves may be also transmitted at least partly in the atmosphere. So what we may see at the balloon altitude is a composite between some Rayleigh waves, some surface waves, plus and a P and SV wave. SV is the vertical component of the secondary wave, of the shear wave. So this is a kind of composite of various signals. So and this has to be, we might be able to see that, and this has to be worked a little bit to know what will be the impedance at the planetary surface. So this is part that I expect of the work that I expect to be done during the workshop. So that said, there are a lot of potential noise contributors for an infrasonic measurement, because I'm not at all a specialist of the Venus atmosphere, but from what we know, it's very dynamic, coming from less than 1 meter per second at the surface for the wind to several tens of meters per second over the clouds, up to 100, I think, 70, 100. And so there are a lot of perturbation expected from the upper atmosphere, which could include the turbulence, the wind, motion of the gondola when you measure the pressure. So that's more local effects. None talking about regional effects that could affect also the measurement we are trying to make. So it includes the acoustic gravity waves, and also potentially the impact of volcanoes on the ground that or storms that might generate infrasounds at distance, just like it does on Earth. So there is a tremendous number of things that may induce perturbing signals with respect to that. And so there is a need to investigate the amplitude and the possibility of this signal and see if we can still get a measurement done. So all in all, infrasonic sensor may be able to record the seismic signal in a bandwidth which is also a wild guess. With some delay, you have to recall that the waves take some time to get up in the atmosphere, so it's there will be also some delay. From an instrument slash system perspective, there are also a lot of questions remaining. What is the optimal altitude? You have seen that depending on the altitude, the attenuation is not the same. But also from a technology perspective, this is not exactly the same thing. So there is a trade technology, system study with respect to that. Another question that might very quickly arise is, what is the best configuration from the sensor? When on Earth we are trying to measure acoustic infrasounds, you need an array. This might be the same case on Venus. Probably, at least at the very least, we need to be able to filter all the waves that come here from here and restrict the measurement zone to upward waves, so that implies at least 2 sensors in order to be able to do a spatial filtering with maybe 10 to 50 meters. It would be better with respect to the waves. 50 meters of difference, so that's basically a fishbowl with your pressure barometer. But that's not a big payload. I mean, a barometer its weight might be less than 1 kilogram. So that's not big. But you have to deploy a tether with a 50-meter tether with that kind of stuff. So this is the kind of question we will have to see. From a more system perspective, we probably need 2 or 3 long-lived balloons with a typical life duration between 6 months, 1 year. This is difficult to say because of the uncertainties on the seismicity of Venus. We need to power them autonomously, solar versus LTG. We need also most probably an overall data management system, just like on the Mermaid concept. We need autonomous, autonomous detection of events, because we won't have all the bandwidth to get back all the data and to process them on Earth. So eventually we have got also to have autonomous event detection, time synchronization between the events, between the gondolas. We probably also need a relay orbiter in order to synchronize all that. So that makes a pretty complicated system. That's feasible. That looks feasible, but that's not easy. Well, the ideal trade, just for the for the record, either we deploy, also if we want to go to deploy a network of balloons, either we deploy a big system with 3 gondolas in the same one, and we count on the dynamics of the Venus atmosphere to disperse them all around the planet, or we can probably use 3 different probes. This kind of trades will have to be done. So that's the second possibility for seismic investigation. The last possibility, and this is more remotely feasible. There is a lot of work being done. Is as you see, to try to measure and to try to find the physical parameter that can be easily processed in the upper atmosphere or in the ionosphere. And this is mostly Phillips and our work. So actually, you can consider several ways of measuring the perturbation when it arrives very high in the atmosphere, typically 150 kilometers. So first, you can probably try to measure directly the atmospheric density variation, directly, in the neutral atmosphere. You can also measure the impact, on the chemical equilibriums in the ionosphere, with some air glow as a consequence of that. And also you could measure the TEC, the total electric content of the ionosphere, because it will also oscillate when the seismic wave will go through it. So, and there are several possible ways that I will go through. This is a kind of a prospective work. Some of them have been done on Earth with some feasibility. I will try to quickly go through. The direct density fluctuation detection, and this is a picture taken from Raphael's work. The proof of concept has been done on Gautier. This is basically Gautier has measured the variation in its drag when a tsunami wave has been propagating after the Tohoku earthquake. So this is a direct detection of the wave by the drag measurement. So Gautier has been able to measure that there is a pretty good match between the synthetics, between the simulation, and what has been actually measured by the spacecraft. Well, actually, this is interesting, but there are a few caveats to take into account. For this was a magnitude 9, so a very, very, very big earthquake in order to measure that. And the other stuff is that you have to have a very good knowledge of either the drag or a very good knowledge of the orbit in order to derive the tiny variations and to filter them in order to get the match. So that's more a proof of concept. But that's that's a proof that it works, actually. And as the atmosphere on Venus is far more important than on Earth, that could be considered. When it comes to when the waves, so that was a direct measurement. Another measurement would be kind of indirect measurement. The idea there is to measure the consequences of the passage of the waves in the equilibrium of the ionosphere. So there are various ways to do that. Here you see one of these is the air glow measurement. When the wave travels, it induces some change of equilibrium within species in the ionosphere, and when they come back to their initial state, they emit air glow. And so this air glow you can measure for various species, so oxygen here. And here you see, for instance, with the same earthquake, the passage of such wave over I think it was the Hawaii Island, it was in the 630 nanometer band. So you see here the ondulation due to the passage of the tsunami, which has induced acoustic gravity waves above the ocean. And this is a paper from Makela et al. 2011, which shows also a very good match between the synthetics with the simulation of the wave propagating upward and the measurements that you eventually get. On Venus, there has been an attempt to do that, typically with Virtis. I think that we talked about Virtis earlier. The local adiabatic temperature perturbations may induce such variation. The issue here is a kind of sampling issue with respect to the wave, because actually you've got your Rayleigh wave traveling at 5, 6, 7 kilometers per second, which is also the speed in low orbit of a satellite, and so it's difficult to catch the wave when you cross, when you both are crossing at the same speed. So you need a very good geometry in order to be able to catch it. So either you get farther from the planet, but you need a better resolution and a big telescope, or you need to find a way to go through that. But there is a dynamics issue here, a system issue, in order to be able to get this kind of measurement. But this is, in principle, this is feasible either during the night with infrared measurement with some species, or during the day with UV. And there is a very good paper about that. So that's a first way to do that. You could also monitor the Keck perturbations by a Doppler sounder. So the proof of concept has been done by Artru et al. In the 2004. So it's also very easy to understand. The HF waves, they reflect in the E and F layers of the ionosphere. So you've got an emitter and a receiver, and if we get back and forth, you are able to monitor the small motion of the ionosphere. And that was done with a CTBT Doppler sounder station in France, in Francourville, with a big earthquake also, but with a high-pass filter, you are able to retrieve the seismic wave in the ionospheric motion. So that's something we could do. And as we've got an ionosphere on Venus, I don't think it's a good idea to put such a station on the Venus ground, but you can imagine that with a swarm of spacecraft, you'll be able to monitor the upper level layers of the atmosphere. So the same principle could be used, although the question is here the resolution versus altitude trade, because I think it's a few kilometers array that was used to detect this variation. So you have to put that in orbit, so that means a swarm of spacecraft. That's a little more complicated, but the principle, but that's very simple antennas. I mean, that's monodipoles, but that's another way we could use, because swarm of spacecraft may be able to be done. And I would say the less sure possibility might be also There has been some work, actually. I would be more precautious with that. There have been several attempts of detecting Keck variations with a synthetic aperture radar, with SARS. I've been part of one of the studies with Onera a few years ago. Our attempt, we wanted to monitor Keck variations. Basically, I'm not at all a SAR specialist, but it was to monitor the coherent scatterers and to take a reference point on the ground and to be able to monitor the coherency of the measurement along a ray. This was difficult on Earth because of it was difficult to maintain the coherency with the trees and all the various stuff that exists on the surface of Earth. But that could be considered maybe for Venus. And also, I think that Franz Meyer has monitored a gravity wave with a SAR. This worked not so bad. With the gravity waves, so it's a variation of Keck that has been measured. So it's here. So this is possible to monitor Keck. The issue here is the resolution that you get, because here it's more the amplitude of the Keck that you are measuring, when what we are trying to do is measure small variation about this global variation of amplitude. So we were into a signal over noise ratio at this point, and so that needs definitely more work. But that's something that could be considered. Last but not least, you will see if you come to Philip's talk, there have been a lot of work at IPGP with the dense network of GPS to monitor the Keck variations. Basically, here the Keck variations were measured through a dense network of GPS that allows to have a lot of piercing points through the ionosphere to monitor all these changes. And I think Lucy has been also involved in that. This concept, is probably difficult to apply to Venus with some kind of CubeSat network or so, but this is also something we might be able to consider. So, in order to conclude, several trades remain for the orbit detection, although they are promising. We are just trying to find a way through all these methods. There are an issue for the permanence of the measurements. Do we use a high orbit, elliptic orbit? What is the number of satellites which are required? We've got questions about the feasibility of the radar-related methods, which might be interesting because radar are things that we master very well. The signal over noise ratio for the night sight measurement for the air glow are also an area of concern. And last but not least, the spatial and temporal resolution to get the sampling of the seismic waves is also an issue, because you probably need something like a kilometer level for the resolution, for the imaging. Maybe less if you just monitor the first arrival of the wave, and you need a temporal sampling which is in the hertz, one sample per second, or one image every 10 seconds. But this is the kind of ballpark where we are. So that's kind of challenging also. To finish, a comparison of techniques, a very, very quick summary that was put together by Jim. So this is the kind of summary where we are right now before the workshop. So 3 options: Venus surface lander from 1 to 3, Venus balloons 3 to 5, Venus orbiter 1 to 3, Venus orbiters. We've got environment which are different, but from this environment perspective, this favors balloons and even orbital measurements. We've got different observables which need each of these way of measuring the seismic waves need a lot of signal over noise study in order to be sure that we'll be able to measure properly the seismic signal. Different levels of maturity, with a very high maturity for for the orbital signal to lower maturity for the ground station. So all in all, seismology on Venus is a very new and exciting challenge, as you have seen, because I've tried to make an overview of that. Although some of the techniques lacks maturity, we are not so far from a realistic technology demonstration. We are not done yet, but we are not so far. And after Mars, Venus is the next piece of the puzzle for the telluric planets history to be unveiled, and we are very eager to go on with that story. Thank you.